Hello, folks. Doing some experiments. I should probably add a little bit more water to both of these. That looks nice. It's pretty. Let's get a little bit more water. Just get it a little topped off. There we go. How you doing there, King Jacks? Hello, Adiaman. Welcome aboard. We'll do some experiments today in the lab. I got my son with me today. I'm a chemist. My son is a physicist. Just thought we'd, have him on board while we're chatting about science and chemistry and life, and I guess a little bit of physics today if you want. What do you guys think of the little YouTube thing there in the back, huh? Is it distracting or you like it? It does make it a little tougher to see the colors, doesn't it? Just a bit. I think it's working, though. We can always move it if you guys want me to. Looking pretty. So yeah, if you're new to the live, I've got some universal indicator in both of these flasks. Universal indicator is also known as rainbow indicator. Thank you there, King Jacks. I appreciate that. Universal indicator is also known as rainbow indicator. Rainbow indicator or universal indicator displays a bunch of different colors at different pH values. How you doing there, AK? And so these are the colors that universal indicator will display at the different pH values. So right now you can see that's like a bluish violet over here and a violet over here. So our pH is pretty high, right? 9 or 10. Watch what happens when I add some acid to the flask. Here we go. Over here on the left, add a little bit of acid. 3 drops. Got a little rainbow action there. And it looks like our pH has relaxed to about pH 6. Yeah, what do you think? Sure enough. And we'll try the same over here on the right. We're going to add a little bit of acid. The acid I'm adding is hydrochloric acid. It's the same acid that's found in your stomach. Got a little rainbow action going on there. Why 3 drops? I don't know why 3 drops. It's just what I'm adding. Looks like our pH is maybe 3 or 4 over there on the right. Yeah. Sure enough. A little bit over here on the left. A little more acid. Let's get the speed turned up here a little bit, huh? There we go. All right, now I'm going to add sodium hydroxide base. Over here on the left. 1, 2, 3, 4, 5, 6. Kind of cool. Same over here on the right. What do you think? You think this setup's a little distracting? There, we got the rainbow. No, I think we're seeing okay. Looks like our pH is about 7 right now. Do you know what that emoji means? I have no idea. I'm too old.
No.
Hello there, Hollywood. Just trying to guess what that emoji means. I can't tell. Looks like a dog or a cat. It's kind of neat. I'm adding more base over here on the right. Now we'll try adding some. Hello there, Hollywood. We're gonna try some hydrochloric acid over here on the left. And let's cut those room lights off there, Jake. I got my son here, Jacob, with me.
That make a difference?
You can see a little bit of what is that, refraction over there on the left-hand side from the YouTube sign.
Yeah, I think so.
Hello, Gigabean. We got a little different setup we're trying today. You know, a little YouTube light there in the back. You let me know if you think that's distracting. It's kind of nice over here. You can see a little bit of a diffraction from the YouTube light I got back there. Yeah, I got my son here with me. He's a physicist. You guys have any questions about physics, you might want to drop them in the chat. We'll do our best to answer them. I'm a physical chemist, but he's a real physicist. He's a Jake, what are you studying again, or what might you be studying?
Right now,
Yeah.
probably like cosmology. Maybe is the. But that's a
Cosmology.
new development, so I don't know how much I can say about.
That's all right. Tell everybody what cosmology is, just so we're on board. I need to remind myself what it is again. What is cosmology?
So the person I'm working with, I guess, is interested in the history of the universe.
The history of the universe.
So especially like the early history, right? Like what happened
Yep.
very early on, Big Bang, after the Big Bang.
Sure. Now I'm always trying to remember, of course, because I'm a chemist. How soon after the big, if I remember correctly, I'm going to ask you here. Maybe you know, maybe you don't. How soon after the Big Bang did we basically have protons, which in my book is a hydrogen atom? So that's going to be. I thought it was within 3 minutes. Is that right, or don't you remember?
That sounds right, but it's. I don't know.
Yeah, drop in the chat if if you Google it and we're off a little bit. I think it's within just a few minutes. I'm guessing within 3 minutes. You got hydrogen, baby. You got the hydrogen atom. Protons. The nucleus of a hydrogen atom. So Adi Amin wants me to repeat after them. And I'm not sure I'm going to do that because, you see, I'm an old guy and I'm not up on slang. So Adi Amin could be having me repeat something that, is going to make me look really stupid. Got some refraction from the YouTube sign. Yep, you can see it. So ESP Solo says, the Big Bang always makes me think. In the beginning was the Word, and the Word was with God. Yeah, I think there's a lot of religious people who, take the Big Bang and the fact that the universe appears to have a start. And a lot of people who are religious kind of connect that to the idea that there was a creator, a God, or whatever you may, who started everything. What's up there, Tony? Good to see you. Adi Amin is assuring me that it's not going to make me stupid if I repeat that. Do you know what that is? Right there?
I don't know what that means.
Y'all look back at what Adi Amin told me to say, and you let me know if that's a good or a bad idea. Good to see you, Tony. So yeah, we're just doing some experiments here. I'm adding acid to both flasks right now. The acid I'm adding is hydrochloric acid. It's the same acid that's found in your stomach. It's just that what I'm adding is like 100 to 1,000 times more concentrated than what's in your stomach. And of course, you see that color shift to red, and that red color tells us that we've got an acid. And the way the pH scale works, if you're 7, you're neutral. This indicator system will be green at neutral. And the further away you get from 7, the less neutral you are. So the further you go below 7, the more acidic you are. The further you go above 7, the more basic you are. Gigabean says, any religion is good, but I prefer facts and reason over faith. Yeah, some folks think that way. Sure enough. Okay, I'm now going to add a drop of base to the left. Here we go, 1 drop. You might have seen a little bit of blue color develop in here. Let's add like 2 more drops. 1, 2. Developing some green on the bottom. You can see blue in the vortex. Is there any acid with 0 pH, asks JSR. Yes. In fact, this acid that I'm adding has a pH that's lower than 0. Thank you there, John. I appreciate that. So yeah, this would probably have like a pH of 0 or something like that. So Brandon asks, hold on, I'm going to add a little acid over here so we can see some color change. Now I'm going to add some base while I'm reading what Brandon asks. What if there is much more past our event horizon, but we cannot see it due to the speed of light? What's 35b light years out if we can only, a billion light years out if you can only see 14 to 16 light years? You want to tackle that one there, Jake?
As far as I know,
Hello, Glenda.
as far as I know, there's no reason to believe that there isn't more stuff out there beyond what we can see.
All right.
So, it seems like a fair question. I don't know what the answer is.
Hello there, Kara. So yeah, so the thing is, I mean, in the philosophy of science, however, I think it's reasonable to say that you know, if there are things that are unobservable in principle that we really can't say much about it, yeah? I mean, science is kind of silent on that stuff. Do you agree or disagree?
I agree with that.
Okay, here Gigabean's got a question for you. If light has no mass, then how does it push stuff? Come on, Gigabean's always asking the great stuff. I'm adding base right now, by the way. Gigabean asks, if light has no mass. Thank you there, Brandon B. Appreciate that. Brandon says, excellent answer from both of you. Right now, I'm going to be adding some acid, and Jake is going to try to answer the question. If light has no mass, then how does it push stuff? And I'm going to try to give it an answer, too.
Yeah, well, so light certainly has, I guess, no rest mass, I think is the term that people use. Which I guess means if you could catch a photon in your hands and hold it still, it would be massless. Because you can't really do that with a photon. Right, it has energy and it has momentum. So I guess when light hits things, it imparts its momentum to things and loses its momentum because, you know, if you think in terms of photons, say, when I absorb a photon, the photon ceases to exist. So I have to pick up whatever momentum or energy the photon had.
Sure. Looks like Royce is saying that light does have mass.
Yeah, so I think that is an okay way to think about it. If light is moving at the speed of light,
it has undefined mass, yeah?
Well,
No?
So
that's the way I think about it. It looks like I'm wrong.
It interacts with gravity, right? Like the light is bent around the sun.
That's what I was going to say. I was going to say, look, so let's go back to the question. If light has no mass, then how does it push stuff? So here's the way I would try it. You know, matter... you know what? I'm not even going to try. I'm not even going to try. So Everyday asks, does light have weight? And John D asks, does it vary based on different spectrums of light, or is it uniform? So I will say that the energy of a photon does indeed depend on its, as you say, spectrum. I will say its wavelength or its frequency. Mm-hmm. So photons that are red have less energy and therefore less momentum than photons that are violet. But, you know, asking the question, does light have mass, is just such a beautiful and mysterious question. And it brings up a lot of, I would say, holes in our understanding is what I would say. But nevertheless, I like to think of light as moving at the speed of light has undefined mass, but it sounds like my son, who's the physicist, doesn't like that answer. Brandon says, it's lower than the scale we can measure small things. Strange things happen the smaller we go. Indeed. John says, that's the word I was looking for. Thanks for the correction. That makes sense, though. Appreciate the answer. I think, John, you're referring to momentum. So It's Me says, is relativity mass a thing? I'm going to add some bass while Jake tries to pull that question off, if you understand it.
What was the name?
Is relativity mass a thing?
They might be referring to, there's this term, I think it's an older term, relativistic mass.
Right.
So there's this distinction that people used to draw between what's called rest mass, which is the mass of an object when it's not moving, and relativistic mass, which is how much mass an object appears to have when it's moving at a high speed. And they're not necessarily the same. When an object moving at high speeds, one of the predictions of relativity is that it will appear to be more massive. So at least a long time ago, people used to make a distinction between these two. Mm-hmm. I think nowadays you'd be more likely to hear someone say that an object has rest mass, and its rest mass is always a constant. It's a property of the object.
Okay.
And when it's moving, it gains energy. Now, we also talk about mass-energy equivalence. So
sure.
I think there's sort of two different equivalent ways of speaking about the same thing. So if by relativity mass you mean relativistic mass, then that's absolutely a thing that people talk about, yes.
Nice. So Tilak asks, what's this live about? All right, Tilak, we're going to tell you. So what I do is, first of all, we chat about science and life. You're welcome, It's Me. We chat about science and life and just all sorts of stuff on this channel. But usually we do science, okay? And then while we're doing the chatting, I have an experiment set up here that I do most of the time. I change it up, but this is what I usually do. I have 2 flasks here that contain universal indicator. Universal indicator is also known as rainbow indicator. It displays these colors depending upon pH, which is how acidic or basic something is. Right now, the flasks both appear yellow or maybe a little yellow-green, and that tells me that their pH is a little bit below 7, 6 or 7, and so they're slightly acidic. Watch what happens when I add some base to both flasks. I'm add a little bit of base over here on the right, a little base over here on the left, and you can see when I added the base, the color shifts to like a green or a blue. And so when you add base, the pH goes up. And when you add acid, which I'll do next, the pH will drop. So GigaBean asks, wait, so if it's moving, it has mass, but if it's stationary, it's massless. So it's both. And GigaBean is referring to photons. So GigaBean's saying, hey, so if a photon is not moving, it has no mass. But when it moves, then it does pick up mass. And then Blake says, you're welcome, T-Lock. Blake says, that reminds me of the inertial versus gravitational mass. Hello, Declan. How you doing? You want to comment on that at all, Jake? By the way, I do have my son, Jacob, here with me. He's he's got his master's degree in physics, and he's currently working on his PhD in physics. He's going to either go into cosmology or high-energy physics, or he may also go into condensed matter physics. All right. T-Lock, we're from the United States. So we're going to go back to the question that GigaBean asks about photons. The question is, wait, so if a photon is moving, it has mass, but if it's stationary, it's massless. So in a sense, a photon can both have and not have mass at the same time. Why don't you try that, Jake?
Yeah, so I guess no one's ever seen a photon at rest, a stationary photon. So as far as we know, they don't exist. The photon's always moving at the speed of light. But we tell ourselves that if you could ever find a photon that was stationary, it would be massless. It would have no mass. And I guess that's what we mean when we say that photons have no rest mass. So yes, I agree with the second half of GigaBean's question, and then I think the first half was, when it's moving, it acts like it has mass. It's affected by gravity. That's why, like, for example, light is bent around the sun. It pushes things. I think that was a question that was asked earlier.
Yep.
It imparts momentum to things, and so there's even an idea I think people have had of, I think this is light, of using like a large sail to catch light from the sun and propel a spaceship forward.
Oh, cool, man.
Or another thing people have done is they've built tweezers out of laser beams to like hold objects in place.
Well, wait a minute. So they're building, I've heard about these. They call them optical tweezers, right?
Yeah, right.
And you're saying that what an optical tweezer does is it uses photons, and those photons impart momentum to whatever it is they want to grab.
Yep.
Oh, I'll be darned.
And you can hold the object in place.
And that's because photons have momentum,
right.
And so they can push things around. Isn't that cool, man? All right, we're going to go to a couple comments here. Blake says, Blake wants to get a PhD in physics, and Blake is applying right now to undergrad. Best wishes in that endeavor, Blake. Yep, you can ask us any questions. Ask Jake any questions on that. And Brandon says, if I could go to the moon in an instant and look through a telescope where I was, I couldn't see myself standing because the distance of the moon is just farther than the speed of light. I got to make sure I understand this question. So Brandon's saying, look, I want to transform myself to the moon instantaneously and look through a telescope where I once was back on Earth. If I did that, I couldn't see myself standing back on Earth because the distance of the moon is just farther than the speed of light. You follow the question? It's a pretty idea-dense question there. Like Green Lantern tweezers, says Roberto.
Nice.
I apologize, Brandon. I'm not sure we understand the question. Brandon says you could see yourself.
Then yes,
I see.
I think I understand the question then.
Okay, you wanna expand on that a little bit?
It gets a little bit hairy when you try and talk about instantaneous things.
Yes.
In relativity, but if putting that aside for the time, I agree with the idea that
the sentiment, huh?
You wouldn't see that you had disappeared yet. I think it takes light about a second to go from the moon to the Earth.
That's
so
roughly
you'd
correct.
have to set up
It's
your
I think it's
telescope
1.25
really quick.
seconds is right, is roughly speaking.
But
So-
so if you could set up your telescope that fast.
All right, JSR's got a question here. When light passes through a glass slab, does dispersion occur? In a prism, we see dispersion of light. That's a question. Both prism and slab are from the same glass. Why doesn't dispersion occur in a glass slab?
Yeah, that's a good question. I think dispersion should occur even in air. I think it should occur. So it would occur in glass and it would occur in air and also in a prism. I'm not super familiar with how to make prisms. I think they might be made of a slightly different material than just glass. But I don't know. I mean, it might even be possible. I don't know if you can see any dispersion
Sure.
in this video.
Well, the rule of
Probably
rage brings up an interesting point. It's not that complicated. Hey, light takes time to get places. So if you get there in an instant, you'd see yourself back on Earth for 1.25 seconds. I thank you, rule of rage. Come on, rule of rage, clearing up the confusion over here. Appreciate that. So T-Lock says, theoretically, yes, but practically no. Setting up the telescope would take long enough for the light to come to you on the moon. I love it.
Maybe you'd have to. Maybe if you went to like Mercury or Venus or something. You have a couple
Anime
minutes.
says, sorry, I'm interrupting you. Anime says, yes, dispersion occurs in every medium. That's why we see different colors, sunrise and sunset.
Yeah, that's a good example. That's a good example.
Is this theobromine? Is that the compound I'm looking at? Saying hello. C13H12BrNO2. I'm guessing that's theobromine, but I don't know. I might be off. Hello. Best option, go to the sun. So yeah, what we're doing here, just got my son with me. He's a PhD student in physics. He's got his master's degree in physics already. He did some cloud physics. Google it. Says, I think you've been on here before, and I think I've done it before, and I know that I shouldn't say the name of the compound now that I think about it. Anyway, what we're doing here, I got my son here. He's got a master's degree in physics, working on a PhD. I've got my PhD in chemistry. It's physical chemistry, so I like to pretend I'm a physicist, but I'm not really. I'm just a chemist. And then, what am I saying? Just a chemist. Look at the beauty we got in front of us from all this chemistry. Anyway, what I've got here, not adding any uranium yapping. So what I got right here is a 2 flasks with some universal indicator in it. Universal indicator is also known as rainbow indicator. Displays these colors depending upon pH. So right now, this has got a pH of 7. This has got a pH of 6 or so. Thank you there, little heart. And I just add acid or base to change the colors. So Rule of Rage is asking my son, hey, you did cloud physics. Did you do plume dispersion and mixing height stuff?
I did not.
Why don't you tell folks what you did?
The work that I did was I was working with a guy at a Michigan Technological University. He has a cloud chamber. Not the cloud chamber that you'll find in like particle physics.
Yep.
Which people use to like watch tracks of particles.
He was building actual clouds, right?
A cloud.
Yeah.
It's better named. It's to actually make clouds.
Yep.
And his goal, Dr. Raymond Shaw was his name, and one of his goals is to, I guess, build a bigger chamber. So far, the cloud chambers that we've constructed don't make rain clouds. They just make like really. Maybe it would be better to call them fog chambers, even.
Sure.
So he wants to build one where you can get clouds that are more representative of what you see in the atmosphere. And so there's this big like national project working on this. And I was doing some like simulations trying to understand better how to do that.
Anime, yes, it does heat the liquid. The chemical reaction that's going on in here does release a tiny amount of heat. A tiny amount of heat, but not enough to really substantially raise the temperature because there's so much water in here. All right, little heart. Do you think the speed of light depends on the direction it moves? Ask. It's me, Satyu. Now, I would Well, not in a vacuum, right? The speed of light in a vacuum is a constant,
In
yeah?
a vacuum, it's a constant. In certain mediums, though, it could depend on the direction you're moving in. I'm not
Correct.
I don't know if I'm familiar with any examples of that. I know that it can depend on like polarization.
Well, let me ask you this, okay? Well, they say when stuff changes directions, it accelerates, right?
Okay.
So we've got a light beam that's heading near a heavy gravitational body.
Uh-huh.
Okay, so you got, you know, it's heading in the vacuum of space, right? And it gets bent by the light, so it changes direction.
Sure.
So it gets accelerated. Why didn't it speed up? Why is it still going at c? 3 times 10 to the 8 meter per second. Yeah, it's in the vacuum of space. But yet, if it gets bent by a black hole, you know, if something changes direction, it's accelerating. So how does a photon accelerate around a black hole but still maintain its speed of c?
So, yeah, that's a good question with a little bit of a weird answer.
All right, let's hear it.
So, you know, people talk about space-time and space-time being curved and space-time curvature being a manifestation of gravity.
Yep.
So they say gravity's not a force, it's just curvature of space-time.
Yes.
So a different way to understand the question you just asked is to say the black hole warps space-time around it in such a way that straight means that what the photon perceives as straight as it's moving is actually a curved path.
So it's not really bending
So
in
it's
space-time.
not really bending. It's traveling in the straightest possible way. And maybe to answer your question more directly, if you were also, like, say, orbiting the black hole, and the photon came from a laser pointer that you were using,
Yeah.
you would measure the speed of the photon to be c, the speed of light.
Okay. So a lot of people I saw in the comments were asking to get the rainbow times 2. I tried while Jake was giving the explanation here. When I imagine a chessboard, says Ennis, Jim Bros and all y'all who are asking to do the rainbow times 2, I'm trying, man. I am trying. When I imagine a chessboard, I can move the pieces on it like it is real, but it is not even as a photon. Is it exist or not? I apologize. I don't understand the question. Jake, do you understand the question?
I'm not sure I understand either.
Yeah, you might have to try again. We apologize. Sometimes that happens. You know, we can get into some pretty complicated questions here, and sometimes it takes a little bit for us to understand, so bear with us. Kara, I'm trying. Jim Bros, nice to have you back. I'm trying to get the double rainbow for you. I'm trying, so you'll notice I got pH nice and low. Here, let's do this. This is kind of fun. This will work. I turn the stir speed off, and then I'm going to add a little bit of bass to both. And we'll see what happens. Oh, yeah. We'll see what happens, okay? You got it, Jim Bros. Does light bend as anime? I think it travels the shortest distance between 2 points. That's correct. We got a little bit of rainbow action going on here. I see some violet. I see some red. I see some green. It's a little bit obscured by... Let's get this YouTube thing out of here. I'm just showing off with that thing. That's all that is. Let's see if we can get these colors back. All right? Turn that off. Get this out of the back.
Well, we've had enough light questions. At some point, maybe you should... you could try putting the arrow behind it, and you can see it change.
Oh, yeah, we should do that. Add francium. I wish I had some yapping. Face reveal. Yeah, Kim Jong. We do that at the end. So it does look like a titration. I don't have any francium. The lowest on the chart, the alkali metal that's lowest on the chart that I've ever added to water is rubidium. All right, so the rule of A says, hey, ask this joke. What happens if the space-time is toroidal?
Well, I think you asked me this question once.
I did?
Yeah.
I don't remember. So it's shaped like a donut, right?
Right.
Okay.
Yeah. But I don't know. I haven't heard this joke before, so.
All right. So here's a joke from the Rule of Rage, folks. What happens if space-time is toroidal? Well, we're waiting for the punchline. If it's toroidal, let me see if I can figure out what the punchline would be. I do not know. I do not know. That's my guess. All right, we're going to spin this one over here on the right, see what we get. It does look amazing. Everything go boom.
Ooh, nice.
Yep, looks like I almost perfectly balanced the acid and the base over there on the right. I'm going to push this back just a bit so we can see the colors a bit better. Yep, if I do that, it's going to help. Push this one back. See, we get that nice white background. What's a neutrino? Nothing's. No curvature besides the space cops eating it. I love it. Well done. Can you drink that, Kim Jong? You can, but it's going to ruin your afternoon. You see, there's 4 different dyes that make up this stuff, and one of the dyes used to be the main ingredient in X-Lax. So, yeah, you can go ahead and do that, but I don't think you're going to enjoy the rest of your afternoon if you do. Is it true that atoms can't touch each other? If not, why does everything have a definite shape? So, is it true that atoms cannot touch each other? Man, so that's a philosophical question. As a chemist, I would argue that atoms can touch each other. And here's why I would argue that atoms can actually touch each other. So if you imagine 2 hydrogen atoms, okay? Each hydrogen atom has a nucleus with a positive charge, and each atom has an electron, which is going to have a negative charge. And those electrons, they swirl around the nucleus, kind of like the planets swirl around the sun. The differences in the atom is that we kind of, it's, you know, based on quantum mechanics, we kind of envision the electrons not really like planets swirling around the proton. We envision them as electron clouds. So they're smeared out around the nuclei. Now, if I have 2 hydrogen atoms, we're going to represent those by my fists, and there's electron clouds around each. When those 2 hydrogen atoms come together, what happens is the electron clouds merge and make a single electron cloud. So in that sense, in that picture of things, the way I imagine hydrogen atoms forming the H2 molecule, in this sense, and I know this is a very abstract argument, but in this sense, I imagine that those atoms actually do touch each other. Hey, thank you there, Jim Bros. I appreciate that. Yeah, I mean, that's what I like doing. I love talking about science with y'all, and I love the questions that I get from everybody. It is very imaginative. Why is lead bad for humans, but bismuth is not? Gigabean, you stumped me. You absolutely stumped me. I do not know that. I don't know the reason. Anybody else know? Gigabean has stumped me on a chemistry question. It happens more often than I'd like. Does anyone happen to know why lead is bad for humans, whereas bismuth is not? If atoms have, Kim Jong says, if atoms have electrons around it, when 2 atoms come close together, won't the electrons collide? Apparently not. Well, no, that we can say for sure that they won't, and here's why. Wait a minute. But they can have opposite spins.
Oh, right.
So what I was going to say is the Pauli exclusion principle would keep 2 electrons from colliding, because no 2 electrons can have the same 4 quantum numbers. And the quantum numbers just tell you about, like, there's 3 that tell you where the electron's located, and there's 1 that tells you its spin. So if there were only 3 quantum... Oh, and by the way, the Pauli exclusion principle with electrons tell you that you can't have all 4 of those being the same. All right? So if there are only 3 quantum numbers that dealt with space, then you could not have 2 electrons collide, because if you had those electrons collide, they'd have to have the same 3-dimensional coordinates. So those 3 spatial quantum numbers would have to be the same in both electrons, and that can't happen. However, there's a 4th quantum number that has nothing to do with space. And that 4th quantum number is spin. So because of that, the Pauli exclusion principle does not preclude 2 electrons from colliding. They can have the same 3 spatial quantum numbers as long as they have opposite spins. Accused Assassin says the electrons don't really touch each other according to molecular orbital theory. I don't know. I'd have to get my physical chemistry text out and read through molecular orbital theory again. It is my understanding that electrons can occupy the same space as long as they have different spins. So that's my understanding, but I haven't sat and prepared, a lecture on molecular orbital theory in the hour before I decided to go live. So Jim Bros is in 8th grade in Finland, and they're just now starting to learn stuff about atoms. Well, welcome to the circus, man. Welcome to the circus. Aren't electron clouds the possible coordinates of an electron? Yes, it's me, but it also incorporates the spin. What are you laughing at?
I'm laughing at the Outer Wilds reference.
You comment. I don't know what Outer Wilds
are they both
is.
spinning the same way? I think they're both spinning the same way, though.
What are?
Are you two?
Yes, they are.
Can you spin them different ways?
I can't. Well, wait. Yes, we can. I'm going to flip one, and then we can have them spin in opposite directions, all right? Or at least to our eyeballs, it'll look that way. This is cheating, I know, but nevertheless, we'll do this. So now, I love it. I've never done this before. Now, I have my 2 flasks spinning in opposite directions. What a great suggestion. Who suggested that, Jake?
Oh, I missed the name.
We'll go back through and figure it out. So to our eyes, at least, these are spinning in opposite directions. I love it, man. The rule of rage says, isn't that how we get quantum entanglement? 2 out of 4 or 3 out of 4 satisfied? I apologize. I don't understand the question. Do you?
I assume that they're talking about the 4 quantum numbers.
Okay, got it.
And I suppose if you have 2 electrons with the same spatial quantum numbers and opposite spins, they are entangled, right?
Say that one more time.
Then they would be entangled. If
Yes.
They have the same. If they have the same. All the same quantum numbers except for their spin.
They'd be entangled then.
Well, if you measured the spin of one electron, you'd know the spin of the other.
Correct. So they would be entangled. Yes, that's right. Yep. Very nice.
So yeah, I think that that's correct.
Thanks for helping us out there.
That's a good question.
Somebody asked, what do I mean by electron spin? Is the electron as a particle spinning? Asks Yo Gender. You want to tackle that one, or you want me to?
It's a good question.
I mean, I can tell you how I answer that in my general chemistry classes, and even in my physical chemistry classes. I'll tackle that one. It works like this. So, just like an electron has charge. It has charge. That is something that is intrinsic to an electron. It is just something that it has. We don't need to say anything else other than the electron has charge. Nobody worries about, well, where's it coming from? In the same way, an electron has something that we call spin. Now, it's called spin for historical reasons because at first, people tried to describe the electron spin property as though the electron was actually spinning. But as people learned more about the electron, and at that point they just called it the spin. But as people learned more about the electron, they learned that it couldn't physically spin because as far as we know, electrons are mathematical points. In other words, they don't take up any space, and something that takes up no space can't spin. So just like the electron has charge, and we don't worry about where the charge comes from, the electron has spin, and we don't worry about where the spin comes from. So Patriot asks, how come the funnels are not the same size? I know they're spinning in different directions, but why is the left one smaller? So here's why. I'm going to turn both of them off, and I want you to look at the size of the stir bars in each. You'll notice that the stir bar in this flask is much bigger than the stir bar in this flask. And so the size of the funnel depends on 2 things. It depends on the size of the stir bar and how fast I spin it. So here, I'll get this one over here on the right spinning kind of slow, and then we'll speed it up. So I got this one here. I'll get this one spinning too. Here we go. Sorry, I'm a little behind on the comments, folks. Hey, thank you there, Phaser. Phaser subscribed. I appreciate that. Every day says I have a school project on oceanic trenches, and they look like this. How do they work? All I know is two lithospheric plates somehow collide to cause this. Well, you're on the right track. Keep learning about it. I mean, that's you get one subducting under the other for sure. You also have seafloor spreading. I don't know if they call those trenches or not, where the seafloor kind of spreads apart. Anyway, I've got this stir bar stirring at a certain rate. You can see the size of the funnel. Watch what happens when I turn up the speed right here. So Natalie wants blue. All right, I got it turned up, and you'll notice that the size of the funnel is larger. AOD says informative and really cool to see. Thank you, AOD. You're welcome, and thanks for watching. Thank you, Kim Jong, for the answer to that question. If you can you go up? You skip my question, ask Matan DK. All right, Matan DK. Let's see if we can find your question. Matan DK. Oh, that's way back here. Here we go. Matan says, I have a school project about atomic theory where I have to talk about scientists that contributed to atomic theory other than Dalton, Thomson, Rutherford, Bohr, and Chadwick. Who do you recommend, Jake? They got a school project on atomic theory. They need to talk about scientists that contribute to atomic theory.
Other than them.
Other than them. Sadi.
Yeah, I was thinking maybe
Sadi. Yep.
Lorentz might have done something.
Well, what about
I think
the relativistic solution to the hydrogen atom?
True. So I guess that'd be what, Dirac?
Dirac. Yeah. Schrodinger.
Yeah.
Schrodinger would work. Heisenberg would work.
Mm-hmm.
De Broglie might work.
I guess Einstein isn't on the list, and he helped
with
convince with Brownian motion.
Sure. So yeah, give him a couple answers there. Okay, all those will work. Kiana, after my son Jacob answers this question, I'm gonna come. Thank you, there, Patriot. I'm going to come back to the question of what's going on here. Okay. So go ahead, give it a Edward Teller. Edward Teller. Did he contribute to atomic theory? I don't know, man. All right, go ahead. Pick one of those and tell them which one they should maybe focus on.
Well, I think of those, the one I'm most familiar with would be Einstein, but...
Okay. Yeah, tell them why they should maybe say how Einstein contributed to atomic theory.
I think it was in 1905, the same year that he published his papers on relativity and the photoelectric effect and all the other things that made him famous.
Sure.
He also published a paper on what was called Brownian motion.
Yep.
Which my understanding is if you look at, I guess, small particles under a microscope in like air or fluid, the particles will appear to like bounce around erratically. I guess sort of like that bubble you can see on the...
Oh, you sure can't you? Yeah.
And Einstein, at the time, people weren't even convinced that atoms existed or not. And so Einstein gave like a theoretical description of what was going on. I believe assuming
it was a pollen grain that would bounce around in water, right?
It was something
I think that's
you could
right.
see,
Yeah.
So that would make sense. Yeah, he gave like a theoretical description of what was going on that turned out to match with observations, and this helped convince people that atoms actually existed in the first place.
That's a pretty big deal.
Which, yeah. So maybe not so much about atomic structure. I think most of the other people listed probably did a lot more for the like structure of the atom, but just their existence in the first place.
I think that'd be a great idea for a science project. Thank you there, Musa. Okay. So there's been a question. So some people are new to the live and they want to know what's going on. So we're going to describe what's going on here. In both of these flasks, I have some rainbow indicator added.
Are we sure these are different directions?
I'm not. I think they are the same. Rainbow indicator is also known as universal indicator. Displays these colors at different pH values. pH just tells you how acidic or basic something is. So where you see green in these flasks, like up here and over here, the solution is neutral. Where you see red, like through here, it's going to be acidic. It's quite acidic. The lower the pH value goes, the more acidic it gets. And up here at the top where you see some violet, it's going to be basic up there. And the higher you get above pH 7, the more basic it gets. The closer you get to 7, the more neutral it is. So 8 is slightly basic, and 6 is slightly acidic. Coulomb's also pivotal, says
you can't argue with that.
Rule of Rage. I guess not. Indeed. So that is what these experiments are. Every day says last year we were introduced to acids and bases once, but it doesn't make much sense. What is it about? So acids and bases, here's the deal. An acid is a substance that increases the concentration of a certain chemical species that we chemists call a proton. It's an H plus ion. You can think of it as a hydrogen atom with a positive 1 charge. And hydrogen atoms with positive 1 charges, when they're in solution, they behave in a characteristic way. And so acids, when you add them to a solution, they increase those H plus concentrations, and that causes some general characteristics in the solution. Bases, on the other hand, they are substances that accept those protons. So acids donate the protons and bases accept them. And because of that, acids and bases react with each other. They're like a perfect pair. You got an acid hanging around, it's going to donate a proton to the base. That's basically the way that it works. And yes, Kiana, I am discussing things in terms of the Bronsted acid-base theory. You're welcome every day. Are you all excited for the SMR in Van Buren? So what's the SMR, Rule of Rage? What do you mean by the SMR? We got a nice little pH gradient going here. The other theory, Kalura, are you meaning the other theory as an Arrhenius acid-base theory, or do you mean Lewis acid-base theory? Nuclear small modular reactor. Rule, I apologize, but I am fairly ignorant on what's going on with that. You can, I would definitely appreciate for you to educate me on what's actually going to go, what's happening there. Yeah, but I live very close to where you're talking about, and I'd be interested to know what's going on. So the Lewis acid-base theory, Kiana, the Lewis acid-base theory, instead of talking about proton, I just got to pause and look at this beautiful rainbow over here just for a second. But the Lewis acid-base theory, that describes acids and bases in a more general way than even proton acceptor and proton donor. In Lewis acid-base theory, an acid is an electron pair acceptor, and a base is an electron pair donor. And by introducing that level of theory, you can describe acids and bases even more generally. I agree, Kiana. We have got some beautiful rainbows going on, beautiful pH gradients. You know, we start down here at pH 10. You can see it go through pH 8, 7, 6, 5, 4, 3 at the top on both flasks. It's really gorgeous. So you, Kalura, you like the Lewis acid-base theory. So It's Me says, do they have different density? Apparently they do. They must. I don't know what's going on there, but every time I get this rainbow effect, it is the case that the violet's on the bottom and the others on the top.
What's all in there?
Well, I guess hydroxide ion. I guess hydroxide ion, maybe that's just more dense. I don't know. I really don't know. Boy, those are gorgeous, aren't they? Really, really pretty. So yeah, we're just chatting about science and life here in the chat. I've got my son with me. He's got a master's degree in physics. He's working on his PhD in physics. The Henderson-Hasselbalch equation has entered the chat. Kim Jong, well, I won't be drinking this because one of the dyes that's in Universal Indicator used to be the main ingredient in X-Lax, and that might end the live in 10 or 15 minutes. Palisades Park, an old reactor, lost its licensing. Now Holtec is in the process for licensing for a new nuclear site. Well, the Rule of Rage, I'm interested to hear what you think about this. I think nuclear definitely is the way to go, right? I mean, the issues that we have with nuclear waste pales in comparison to what's going on in our atmosphere with carbon dioxide. So I'm all about going nuclear, but I'm happy to hear if you have a difference of opinion on that. Thank you there, Phaser. Not be drinking it there, Phaser. Add some sugar. Kim Jong, I don't have any. What's in the solution? So Mahit, what's in the solution is universal indicator. It's also known as rainbow indicator. It's just a mixture of chemicals that changes color depending upon pH. You got your master's in nuclear and mechanical, so you could say I'm invested. That's okay. I don't care. What do you think? Do you think we should get it here or not? I mean, I'm thinking yes, but if you tell me no, I'm very interested to hear why we shouldn't have nuclear. Anyway, in these flasks, we have rainbow indicator. It displays different colors depending upon pH. So if you look here, you can see that up here at the top, it's pH 3. Down here at the bottom, it's pH 10. And what's really fascinating about this is that the pH scale goes on powers of 10. So every time you see a change like this, like a pH of 6 is 10 times more acidic than a pH of 7. So every step in the scale, as you go this way, is 10 times more acidic. No, Gigabean, you're not banned from the chat. There's just a lot of comments coming through, so I apologize. I'm not getting to yours as rapidly. Anyway, so here I've got a pH of 3 and a pH of 10 all in the same flask. Yes, Kiana, it is phenolphthalein. So because of this, the pH 10 is, or the pH 3, I should say, is 10, 100,000, 10,000, 100,000. I got that right? 10, 100,000. 10,000, 100,000, a million. Oh, 2 steps. That's why. 2 steps there. 10, 100,000, 10,000, 100,000, 1 million, 10 million. 10 million. So the difference between the top of this flask and the bottom of this flask has a difference in acidity of 10 million times. It's crazy. Absolutely crazy. All right, I'm going to mix them now. And as I mix these, if the concentration of acid and base are the same, then we will neutralize it. We'll see a green color. If there's more base, we'll see one of these colors. If there's more acid, we'll see one of these. Let's see. Let's see. I'm thinking more base, but perfectly neutralized. Maybe a little bit acidic. It's me, 10 million times more protons, H plus ions here at the top than at the bottom. You can also say there's 10 million times more hydroxide ions down at the bottom than there is at the top. All right, put the heart emoji color in the chat that you think this solution will change if I turn on the stir bar. Drop the color of heart emoji that you think this color will change if I mix everything up. I've got a red. I've got a brown. Ain't going to go brown, buddy. Couple brown. I got a green. I got a light blue. Lots of people are guessing red. Lots of people are guessing green. I see an orange. Gigabean. Teddy Tube, Kim Jong, all say green. Kiana says red. Phaser says orange. Let's turn it on and see what happens. Here we go. I'm guessing green for the record. Mohit, guess yellow or orange. Lisbeth, blue. JJ, red. It's me. It's like a yellowish green. A yellowish green. Okay, so we're going to go ahead and in a couple minutes here, we're going to flip the camera around. I've got my son Jacob here with me. He's got a master's degree in physics. He's earning his PhD in physics. We'll talk to y'all, answer any questions you guys might have about science or just life in general. So we're going to be doing that here soon. We'll do a few experiments here, but we're going to be wrapping it up here. Lime every day. You got it. See if we can get the rainbow effect going again. How to get a PhD? Why don't you tell them about that, Jake? Why don't you tell them your experience? It's me asking. How do you get a PhD?
I guess you go to school for a long time.
Yeah, sure you do. But what goes on? Like, how's it different than, say, getting a college degree, like an undergraduate degree?
I guess in college maybe it's more about the classes you take
Uh-huh.
and what you're learning in the classes. And in a PhD, at least in my experience, I guess it's been more about trying, especially as you get deeper into the degree, it's more about preparing you to do research. So at some point classes become less important. You find an advisor who's, I guess, published a lot before and has a faculty position, and you work with them on a project or
Yeah.
multiple projects and try and learn how to, I guess, what that's like and how to contribute something.
Yeah. And you're
And
hoping to
then,
go ahead.
well, and at some point you'll have completed a project or enough projects that you can write it up and talk about it in front of people.
Yeah.
And that's what you do at the end. Is you do that, and if they think you do a good job, then you get a degree.
Then they call you doctor.
Yeah.
And what do you think you might study?
Well, I guess right now I have a couple options. I might work with a guy who's doing cosmology.
Uh-huh.
So he's studying like the history of the universe, especially like earlier stuff.
Okay.
He also was interested in like just gravity more generally. So I guess when people say gravity, think like general relativity, space-time, black holes, that kind of stuff.
Sure.
And the other guy's doing condensed matter physics, and I'm newer to that field, so I don't know how good of a job I can do explaining it.
So condensed matter physics, that's just like what goes on in terms of the physics of like at the atomic level or maybe even lower than that in solids.
Yeah, right.
So tell me something. You told me something pretty cool about that. Like, we know the electron has a certain charge, and we think that charge is like fundamental, so we call it -1.
Uh-huh.
But apparently there's some solids that do something weird with that.
Right, yeah. So there are certain materials, I think it's gallium arsenide it's called.
Uh-huh.
People have found ways to put electrons in these materials, and by choosing the environment really carefully, they can get them to split up to appear to split up at least into a bunch of smaller particles. So they'll have like a charge of 1/7, which is not something that we really thought was possible.
So it's almost like you've split the electron into 7 pieces.
It acts like it's been split up into 7 pieces.
What the heck, right?
Of course, if you try and like catch one of those pieces, you'll just find one electron. So it's not really split up exactly.
Huh.
But
it behaves as though that's going on.
It behaves like it's a bunch of split up pieces.
Yeah, that'd be fun. Electron. That'd be fun to study. That sounds like physical chemistry to me, to be honest with you. But hey,
maybe it is.
Maybe it is. It probably is. I'm sure there's some physical chemists that are studying that. So Kiana asked, "Do you know about microfluidics?" I don't. I can't help you.
Microfluidics either.
Yeah, you may.
It's a good question.
Sure. Yeah, I apologize. I don't know.
Something.
I think you're talking about things like where people try to measure, like say the pH of a cell. So very, like just trying to probe very micro small environments. Is my guess?
A living cell.
Yeah. Oh yeah. There was a guy at Michigan when I was getting my PhD there. That's what he was doing. He was like, he was. He's trying to find the pH of a single cell, like the contents of it, stuff like that, which is crazy. Yeah, chartreuse. Sometimes I do. Thank you there, Kiana. Yeah, very cool stuff. Very cool stuff. What was his name? Oh, he taught statistical mechanics. His name escapes me. I want to say it begins with a K, but Gigabean. I might do one tomorrow, but most likely it'll be next weekend. So Mohet has a question. In organic chemistry, is there a limit to the catenation carbon exhibits? As far as I know, it's going to be 5, right? It can, and that's only for a very short period of time. What do I know about quarks, Kiana? I know that they make up protons and neutrons. I'll go about once a week, Kim. Gotcha, chartreuse. Can you somehow make it another color than lime? Well, I think I have, right? Lisbeth? We've got violet. We've got all sorts of colors in here. Why is organic so hard? I apologize. I got to be honest with you. Organic wasn't that hard for me. I just got it. I mean, I just understood it. Now, it took me, I would say it took me a bit, but once I got the idea, the concept of chirality, I kind of got the idea of what they, how they wanted me to think. Once I understood chirality, for me, organic was easy. But I will say that most people think organic's hard. First of all, because you have to memorize a lot. By the way, there's a color other than lime for you. I got some blue. The other thing is you have to be able to think three-dimensionally in your head. So you have to be able to manipulate, molecular structures in your head. And yeah, I mean that, not everyone can do that easily. But with some practice and with the use of models, I think people can do so. Phaser asks, aren't things basically infinitely small? Because think about the smallest thing you can think about. What is that made of? And then what is that made of? And then what is that made of? So, Phaser has asked a very interesting philosophical question. I'm going to give you my answer, and then I'm going to let you have Jake give his answer. So, I'm going to go to the philosophy of science. In the philosophy of science, we basically say, look, we're going to observe stuff, and then we're going to try to explain what we observe. And as far as we know right now, we have experimental empirical evidence that there are things that are called quarks and other basic physical particles that make up protons and all the other stuff that we ultimately see, like atoms. And so because that is all we can observe empirically, we say that's what it is at this point. Now, we're not sure. It could be that there are things that are smaller than quarks, or what we currently understand as elementary particles. But because we have no physical evidence for anything smaller than that, we say our best guess right now is that matter actually does stop. There's an end point to it. There's a basis to all of matter below which we cannot go. Okay. What do you think, Jake?
I think I'd probably say something similar.
Yeah?
There's, at one point in time, people thought that everything was made up of atoms, and that was it.
Yep.
And then they discovered electrons, and they realized that atoms were made up of things.
Yes.
But then they thought, okay, well, atoms are made up of a positively charged thing and a negatively charged thing, and that's it. They called the positively charged thing the nucleus.
That's right.
And then it turned out the nucleus was made up of things.
Neutrons and protons.
Protons and neutrons.
Yeah. So neutral stuff and positive stuff.
And now we say that protons and neutrons are made up of quarks.
Quarks, that's right. So but the electrons are just electrons, as far as we know.
Electrons are still just electrons. So it seems to keep going.
It does.
But I will say that at every step it gets simpler, right? You think about all the elements on the periodic table.
Huh.
If you call those all the atoms, right?
So wait a minute. You're trying to tell me that you think all the elementary particles is simpler than the periodic table?
Well, there's only a handful of elementary particles.
All right. Okay. All right.
There's quarks, gluons, electrons, muons, tauons, neutrinos. There's 3 different kinds of neutrinos, and then you have like photons and W and Z bosons. Unless I missed one. Oh,
sure.
Higgs boson.
Yep.
And that's it.
So nice. So I like this. Mohit says, in a way, quarks is the resolution limit of the universe. Yeah.
Maybe so.
I think so. Yeah. All right. We're gonna flip this. We're gonna flip this around. We're gonna talk to you for a bit. Pop that on. Get in. Here we go, baby. Come on in, Jake.
Let me get a seat.
So.
Come over here.
Who were your most influential educational figures for each of you? So Taylor asks, who are your most influential educational figures for each of you and why? So while I'm answering this question, and then when Jake answers this question, if you just want to pop some names in the chat that, are your most influential educational figures, you might want to pop those in as well. So probably my most influential educational figure, I have 2 of them. One of them was a professor I had in chemistry when I was an undergrad. His name is Dr. Emmerich Schultz. He taught me at Bloomsburg University. I had him my sophomore year, and he did he did chemistry experiments in class. And I had never seen live chemistry experiments before. And I was blown away, man. I was blown away at the beauty of the experiments that he did. And not only that, but how he could explain what was going on. So not only you got to see this beauty, you also got to understand what was happening. So for me, that was that's just what I wanted to do. I saw him do it. I'm like, that's what I'm going to do. I'm going to do experiments for people. So, yeah, it became a dream of mine. So thank you for being here and, help me live my dream because I got to do some experiments for you today. All right, Jake, you're up. What do you think?
Most influential.
Get on in the screen so I can see you.
Figure?
Yeah.
Most influential? I guess I'd probably have to say you.
Come on, man. Oh, that's awesome.
I mean, right, like these experiments you're doing now, this was like every day when we were kids. So.
Yeah, we did. And you know what? This kid has influenced me educationally as well, now that I think about it, because he was always just so interested in doing experiments, and he made me, I was curious, but this guy is so stinking curious, and he really helped me develop a curiosity that's just been profoundly helpful in not only me as an academic, but also in my life as well. I look pretty young for my voice. Well, thank you. I appreciate that. So Soli says Alexander Graham Bell. Gigabean says, will you post a video tomorrow? So actually, I put a video out today. You guys got to check it out. Go check out my new short that I put out. I made this experiment where it looks like I made a snail, like a metallic snail, and I named him Squirt. So check out that video. It just came out, a short today. Did he set the ceiling on fire? Says Soli. So Soli, I want to hear a little bit more about your teacher that set the ceiling on fire. So Chartreuse says, Mr. Cromartie. As for science, none. The teachers hated Chartreuse. I kept asking questions. That's this kid right here, man. He kept asking questions. I loved it. Taylor, thanks for the question. That was cool. So Rule of Rage, he and I had a discussion a little earlier. I assume you're he. So they and I had a discussion earlier about nuclear. Rule of Rage is apparently a nuclear engineer. And, I kind of made the comment that I think nuclear is a good idea, especially as we're, dealing with climate change and the amount of carbon dioxide that's in the atmosphere. I said, yeah, I think, nuclear is the way to go. And Rule says nuclear is the cleanest and safest power generation we've ever had. It is scary, but no one hears about the cobalt mines. So, getting cobalt for batteries is a real issue. Fiberglass from windmills, etc. So nuclear is probably a good way to go. Kids do have no filters. You know it, Mahit. At the end of the year, my chemistry was super. I can't understand that.
I think you said one of the.
One of the five that passed your class. Got you there. Helion Energy. Well,
I've heard of them, I think.
Yeah, Helion Energy. Anything else you want to say here? You had enough? It gets kind of long, doesn't it?
It's fun. This was fun.
It was fun. I have a good time.
I really like people had really interesting
They
questions.
do, don't they?
Yeah.
They really do. Yeah, it's a lot of fun. So hey, thanks for hanging out.
Things too, so.
I got to get up and get moving. I'm old. If I sit here too long, I stiffen up. So I'm doing great, Kang. I hope you're doing well too. We're gonna call it a day. Mahit, thanks for joining in. And hey. Take some time, look at the beauty that's around you. The beauty of science is everywhere. Check out those sunsets. Check out those sunrises. Watch the clouds. Listen to the drip of the faucet. It might show you something interesting about the world. And thanks for joining in, and we'll see you.